In the previous video, we learned how water can use its ability to form ion dipole attractions with ionic solids in order to actually separate, or more properly, dissociate the two ions from each other, resulting in the dissolving of an ionic solid such as NaCl. We also learned that certain ionic solids, such as calcium carbonate, that possess stronger ionic bonds are much more able to resist being dissociated by water and therefore do not dissolve, at least visibly, within a solution, forming what we call a precipitate. The purpose of this video will be to use this table that we have here in order to show us how to predict whether a substance will more or less be able to dissolve completely within a solution of water, or whether a substance will not appear to dissolve at all because of its poor or low solubility. So the way that this table works is relatively simple. We recognize that an ionic compound is made of a positively charged ion and a negatively charged ion, and we simply match one cation with one anion, and based on experimental data collected over however many years, we can predict with reasonable certainty whether we are not going to see any precipitate form, or whether there is an expected precipitate that is visible. Now, the easiest way to make use of this table is actually to take a look at a few double displacement reactions and see what kind of precipitate is formed, if any. So take note that all of the aqueous solutions that we start with in our reactants are all assumed to be colorless and transparent, meaning that there is no precipitate visible. So if we treat each of these as a double displacement reaction, we can simply take the cations or the anions in both of our compounds and simply flip them. So sodium would then be paired with sulfate, the formula for which we can write here. I'm skipping over how to write the chemical formulas so that we can focus on using the solubility table. But remember that you will be required to determine the chemical formula of missing products when constructing and completing reactions yourself. So if sodium and potassium switch places, sodium would end up bonded to sulfate here, and potassium would end up being bonded to chloride, and we can quickly balance this reaction by putting balancing coefficients of 2 to balance out potassium and sodium, and our initial reaction is done. So if we use the data table, we can recognize that sodium and potassium are both alkali metals, and we can see that when alkali metals pair with basically every possible anion, they produce soluble substances, meaning that we are not going to see a precipitate here because sodium and potassium are both alkali metals, and therefore these would remain dissolved in water. So here, we do not see a precipitate forming, but because all of the solutions were colorless and transparent, and we are making two substances that dissolve in water and also are colorless and transparent, we should not be able to see any observable change in the reactants here, and therefore, even though these are the products that we would expect to see, we would actually see no visible reaction take place because all of these substances are still dissolved or dissociated within water and would actually exist as separate ions. However, if we take a look at this equation here, silver nitrate being mixed with hydrochloric acid, we can do the same thing. Let's switch our cations. So we're going to switch silver and hydrogen so that we get AgCl, silver chloride, and we actually get a different acid here. So instead of HCl, we would get HNO3, which is an acid, nitric acid. Now, something interesting happens when we use our solubility data table here, because if we look for the the ion silver here, we can see whenever silver comes up, so silver comes up here, silver comes up here, and what we're looking for is silver paired with chloride, which we see right here, and we can see silver paired with chloride has very poor solubility, meaning that in this case we would have a precipitate forming because silver chloride doesn't dissolve very well, so we would see this as a solid, or at least some sort of powder that forms within the solution. Now, if we want to check whether this acid, nitric acid, would be visible, again, we can see in any situation where the hydrogen ion is our cation, is pretty much going to result in a soluble product being produced. So even though nitric acid is able to dissolve in water, we can clearly see that we have our precipitate, and therefore there is an observable change that we can see, which means there is actually a chemical reaction that has taken place because this new precipitate clearly identifies that a new compound has been made. Now, the most challenging variety of this particular example is where we're not actually given the chemical equations or chemical formulas of our reactants, and we need to figure them out for ourselves. So here's strontium hydroxide. If we know that strontium is an alkaline earth metal with a positive 2 charge, and hydroxide is simply OH minus, our chemical formula for strontium hydroxide is going to be SrOH, and in brackets 2 here. Now, we're told that it is a solution, so we're told that this compound is dissolved already, and so we can write the state of matter aqueous here. And in this case, we are doing a neutralization reaction because we're going to be reacting strontium hydroxide, which is clearly a base, with phosphoric acid, and we can tell that this is an acid because it's dissolved in water and it contains a hydrogen that can be easily removed. So we know that every neutralization reaction is going to produce water when the H plus and OH minus react together, and our salt that we're going to make is strontium phosphate, for which we can calculate what the chemical formula for this would be, because strontium has a positive 2 charge, phosphate has a negative 3 charge, lowest common multiple is 6, 2 times 3 is or positive 2 times 3, positive 6, negative 3 times 2 is negative 6, positive 6 minus 6 is 0. So in this case, we only really have to figure out whether this compound is going to be able to dissolve or form a precipitate, because our other chemical is, of course, water here, which we know is going to be a liquid. So if we go up here, we can actually look at the anion, which is actually easier to start with. So we're going to start by looking at phosphate, and we can see if phosphate is paired with an alkali metal, H plus, or ammonium, which is the polyatomic ion NH4, it is soluble, but all others, which does include strontium, are going to dissolve very poorly in water, which means if this doesn't dissolve completely in water, we would see this solid form, and therefore we definitely know that a precipitate has been produced, which shows us that there is a clearly observable change in that this precipitate did not exist before in the reaction. Now, because of the fact that, number one, ionic solids dissolve and the ions separate when they are put into water, there is no visible reaction if the products are also completely soluble, because all of the ions would stay separate within the solution. But when a precipitate forms, that isn't actually true. And the conclusion that we can say is that reactions without a precipitate that form effectively do not occur, because there is actually no change that occurs to the separate dissociated ions in the reactants. To test your ability to use this solubility predictor data table, you can try the practice problems at the end of this review package here, and in the next video we're going to explore a third complication to double displacement reactions, situations where a second reaction occurs immediately after the displacement reaction.